This conference will now be recorded.
Hello everyone. We will start with problem, but after that there will be discussion related to formation of colored ion tendency for D block elements and their magnetic behavior, and also the tendency to form complex, and there will be also the related problems. And the first problem. The correct order of following 3D metal oxides according to their oxidation number we have to find out. So how many oxide examples are given? Total 5, A, B, C, D, E, and we have to find out the order. So first we will find out the oxidation state. The first oxide is chromium trioxide. So for each oxygen it is -2. So for 3 oxygen total negative charge will be -6. That means overall positive charge over chromium it must be +6. Then for Fe2O3 total negative charge is -6, but you have 2 iron, so that is why individual iron will be having oxidation state +3. So chromium having oxidation state +6, then iron having oxidation state +3, and MnO2 it has total negative charge -4, and this is +4. So that is why Mn will have oxidation state +4. Total negative charge for V2O5 for each oxygen -2, 5 oxygens it is -10. So per vanadium it will be +5. Vanadium having oxidation state +5. And then for copper it is total negative charge -2. So per copper it will be +1. So here maximum oxidation state we can find for chromium, that is +6. After that it will be vanadium, then Mn and iron, and at the lowest there will be copper. Now in options 1, 2, 3, see, all are having E. So what is the previous one? In both option 2 and 3 it is B. Now B is iron. So both are actually correct. But if you move to next one, that is D or C. Now D is +5 and C is +4. That means which one will be correct option? That is among 2 and 3, any one of these will be correct option. Because up to, that is if we consider the last two, it is same, E and B. But then we have D and C. D and C means +5 and +4. Okay. So +5 and B is iron, which is +3. So it is A, then B, C, D, and copper will be E. But maximum is A, after that D, then C, B, and E. So it is matching with which option? A, D, C, B, E. Matching with option 3, right? Option 3 is the correct option. Second question. Iron exhibit +2 +3 oxidation state. Which of the following statements about iron is incorrect? There are total 4 statements. All these statements are related to iron. One of these 4 statements is wrong. That we have to find. The first statement is saying ferrous oxide is more basic in nature than ferric oxide. So ferrous oxide means oxidation state of iron will be 2. So the formula is FeO. But for ferric oxide it is Fe2O3. Now it is saying that ferrous oxide is more basic. Now whether the first one is more basic or not, how to understand? Just find out oxidation state. Here oxidation state is +2. Their oxidation state is +3. Now when oxidation state is high, it will be more electron deficient. That means if you compare Fe2 plus and Fe3 plus, 3 plus is electron deficient. So that is why it will be towards acidic, it will have acidic nature more, and it will be having basic nature. So basicity for Fe2 plus, it will be higher. So this statement is correct. And this is not just true for iron, it is for in general any metal. That is, if the same metal having two different oxidation state, always the lower oxidation state, as it is more electron rich, it will be more basic than the other one. So this statement is true. Second statement, ferrous compound. Ferrous compound means iron compounds where iron is having oxidation state +2. Those are called as ferrous compounds. They are relatively more ionic than the corresponding ferric compounds. Ferric compound means Fe3 plus. Now, when oxidation state is high, same metal, oxidation state high. So always the lower oxidation state, that will be more ionic. Fine. So that is the reason this will also be correct. The third one, ferrous compounds. That means again compounds where oxidation state of iron 2 plus. They are more less volatile than the corresponding Fe3 plus compounds. Now just that is directly from any logic, you cannot understand it whether it is correct or not. But whenever you are facing this type of problem, that is whether it is correct or not, just move to the other statement. Because if you are sure about the statement 4, whether it is wrong or not, then easily you can choose the correct option. Because 1 and 2 we are sure, and 4 if you are sure, then you can easily understand which option will be the correct option. The fourth statement, ferrous compounds are more easily hydrolyzed than the corresponding ferric compounds. Hydrolyzed means reaction with water. Fe2 plus will be having more tendency towards water, or Fe3 plus will be having more tendency to react with water. See, here Fe3 plus is having higher oxidation state. That means it is more electron deficient. So that is why hydrolysis with water, that will be facile in case of Fe3 plus, but not Fe2 plus. But here it is mentioned that ferrous compounds are more easily hydrolyzed than the corresponding ferric compounds, which is actually not correct. The reverse statement, that will be correct. That means Fe3 plus will be easily hydrolyzed because their oxidation state, that is high, more electron deficient. So this statement is actually false, and we have to find out the false statement. That means this will be the correct option. So see, this type of situation you may face where if one of the statement, if you are not sure about, just you check the other statement, because if you are sure about the other three, you can easily choose which option is correct. So here we have to find out the wrong statement, and wrong statement is the fourth statement. So any doubt in these two problems? Should I repeat any part? So ferric compounds more easily hydrolyzed than the corresponding ferrous compounds, and it is because of the high oxidation state, that is high positive charge. Fine. In context with the transition elements, which of the following statement incorrect? That means all the four statements that are given all are related to transition elements, and we have to find out the wrong statement. One of these four statements will be not correct. First statement, in addition to the normal oxidation state, the zero oxidation state is also shown by these elements in complexes. These element means transition metal we are talking about. D block elements, if we see carefully, variable oxidation states are possible. Okay, but that doesn't mean that in zero oxidation state it cannot form complex, though we have not discussed yet. That is the complex formation tendency. But just think about iron, not iron, that is any metal carbonyl complex. That is simply carbonyl is present, no other ligands are present. So I'm writing in general M and CO. Suppose total X number of carbon monoxide are there. So this is metal carbonyl complex because you have only carbon monoxide as ligand and no other ligands present. And CO is neutral, and overall the molecule is neutral. That means metal is having oxidation state 0. That means 0 oxidation state is also shown by these elements, and this statement is correct. So this is true. Second statement, in the highest oxidation state, the transition metals show basic character and form cationic complex. Now remember, in the previous slide, the second question what we have discussed, whether Fe2 plus is more basic or Fe3 plus is more basic. It is Fe2 plus which is more basic because it is having lower oxidation state. But here it is mentioned that the highest oxidation state, the transition metal will be more basic. That means when the metal is same, suppose you have two metal, one is M plus, another one is M2 plus. So which one will be more basic? It is always the lower oxidation state that will be more basic. But it is written here highest oxidation state. That means among these two, M2 plus is highest. It will show basic character, but that is not true. So this statement will be the wrong statement. See, if you are sure about that this statement is wrong, without even considering that statement, you can easily choose which option is correct. It is not that always you have to, if you have time, that is fine. But if you do not, you are lacking in time, then if you're sure about any statement, you can easily choose this. And there is another part also in this statement. They will show basic character. That is not correct. It is also mentioned that they will form cationic complex. That means it is in higher oxidation state, they will form cationic complex. Now cationic complex means overall if we consider the coordination sphere, outside there will be positive charge. Now if outside there is positive charge, that means it may be +2 +3. That means the metal should have very high oxidation state, and some of the charge for this metal that will be balanced by the ligand that is present inside the coordination sphere. But still some excess positive charge present means metal should have high oxidation state. So if you consider only this part, then the statement is there is nothing error. But the first part of this statement is not correct. So even if it is partially correct, you cannot say that it is completely correct. So ultimately it is wrong. So option 2 will be the correct option. But what about the other two statement? Why these two are correct? Let's see. In the highest oxidation state of the first 5 transition elements. What are the first 5 transition elements? Scandium, titanium, vanadium, chromium, manganese. So in the highest oxidation states of the first 5 transition elements, all the 4s and 3d electrons are used for bonding. Now scandium is 3d1 4s2, titanium 3d2 4s2, 3d2, basically one electron will be gradually increased. Then 3d3 4s2, 3d for chromium, remember there is one exception, it is actually 3d5 4s2, and Mn is 3d5 4s2. Now maximum oxidation state, if we consider, for scandium you can remove all the 3 electrons, so it will be +3. For titanium you can remove 2 electrons from here and also 2 electrons from 3d, so it will be +4. For vanadium +5. For chromium +6 oxidation state possible by removing all the electrons, and for Mn we know it is +. That means maximum oxidation state you will be achieving only when you are removing all the 4s and 3d electrons. And up to manganese there is no pairing occurring, because maximum capacity for if you consider d orbital, you can place 5 electrons, and up to Mn there is no pairing, and as there is no pairing up to manganese, that means you don't have to break any pair. Now suddenly when after Mn, when you are having iron, now one of the, that is the extra electron, now there will be pairing. Now see, this pair you cannot break, so now you have only 4 unpaired electrons. So now you cannot say that maximum oxidation state of iron you can achieve by removing all the electrons. That is not, you cannot say that, because we cannot break this. But up to manganese there is no pair, so that is why it is possible. So this statement is basically also correct. This is true, and second statement false, that we have already seen. And the last one, once the D5 configuration is exited, that is over, the tendency to involve all the 3d electrons in bonding decreases. Now see, if 3 is true, obviously 4 will also be true, because when you are moving, that is beyond D5, when you are having D6, D7, now the tendency to involve all the 3d electrons not possible. Just see the example that I have given for iron. Now you cannot remove all the electrons. Okay, so this statement, it is also correct. So here correct option, that means the incorrect statement is, sorry, it is the second option. Okay, any doubt? So now we will see another topic, which is formation of color dyes. So for D block elements, this is a very unique property which you will not find in case of other block elements. And what is that? It is a formation of color. Now we have to understand why the ions given by D block elements, why they are showing color. Okay. Most of the compounds of transition metals, that is the compounds that you can get for transition metals, it may be complex, it may be any salt, they are colored in the solid form or solution form. So if you simply take the solid compound, it may be colorful, or if you are making some aqueous solution, then also it can show color. But this type of property, unlike the compounds of S and P block, you will not see, because mostly they are white. So why they are having such unique property, that we have to understand. Now some primary idea about crystal field splitting we already have, and here see, when it is free ion, that means suppose you have any metal ion M2 plus and there is no ligands present, that means it is free ion. So when it is free ion, all the d orbitals, that is 5d orbitals, dxy, dxz, dyz, x square, y square, dz square, all these will have same energy, that means degenerate. But when they are in presence of some ligands, it may be tetrahedral environment or it may be octahedral environment. Now there will be some, that is the degeneracy will be lost. And now you will have two different set. In one set, Eg, which is having higher energy, these two d orbital will be under this set, and the lower energy set, which is T2g, these three will be having in this, it will be considered under T2g. And what later it is completely different, but now we will focus only on octahedral. So the color of the compounds of transition metals, it is because of the presence of incomplete N-1d subshell. Now N-1 means the penultimate shell, because the outermost shell it is for first transition series. Ns is basically 4s. So if Ns is 4s, that means N-1d, that will be 3d. So in 3d, there is incomplete, that is all the, some places are vacant. Okay, so it is incomplete resorption, and that is why electrons can jump from lower energy to higher energy, and that is the reason if that particular energy falls in the visible region, you will be able to see color. So in case of compounds of transition metals, the energies of the 5d orbitals in the same subshell do not remain equal. So this is because of this crystal field splitting, because when ligands are present, now you will have two different set Eg and T2G. So they are not having same energy. Now under the influence of the approaching ion towards the central metal ion, that means the environment of ligand. Okay, the d orbital of the central metal, now there will be splitting in two sets, Eg and T2G. Now suppose we have this type of configuration. This is T2G, which is containing total 6 electrons, and this is Eg, which is containing 3 electrons. So it is T2G 6, Eg 3. Total number of d electrons, it is d9. Now d9 is basically copper. So for this type of arrangement, here one of the electron can jump from T2G to Eg, and the energy of this particular that is this energy gap, if it falls in the visible region. Okay, and suppose the energy of this particular color, that is here in this case it is the yellow color, because it is the band in the visible region. If you consider that only the visible part, then among these different colors only the yellow color is absorbed, because this energy gap between Eg and T2G, this daily value, it is matching with the, that is a corresponding frequency that is matching with the yellow zone. So the energy of this particular color, it is just perfect, that is just right to promote the electron from lower energy to higher energy. That means energy in this zone that will be absorbed. So if this color is absorbed, rest of the portion, that is this portion and this portion, these colors will be not absorbed. Now if these colors are not absorbed, that will reach to our eye. Now if you are thinking, then there are so many colors, red, orange, then light blue, deep blue, purple, then which color we will see? Actually, when the rest of the part which is not absorbed, what happens? You will see the combined effect of all these colors. So if you mix all these colors, down and upper region, the overall combined color you will be able to see. Okay. So white light, which is basically ordinary sunlight, if it passes through metal ion solution, some wavelength in the light will be absorbed. So in the previous example, you have seen yellow zone is absorbed. If a particular color is absorbed from the white light, because white light is mixture of all the colors, and if you are that is only particular zone is absorbed, now what we will see, our eye will detect by that particular color, which you will get by mixing of all the wavelengths of light. So by mixing the remaining color, the overall combined color that will be generated, our eye will be able to see only that color. So this color is called complementary color. Fine. So copper 2+ ion, which is absorbing light in the red region of the spectrum, and we see this mixture of all the other wavelengths as pale blue. So in the previous example you have seen their yellow zone is absorbed, but if you another example we have seen, which is copper 2+. So in solution it will absorb light in the red region. Now if it is absorbing only the red region, so except red, rest of the colors will be mixed, and it will give you the color cyan. Cyan is light blue. Okay. So when it is white light, that before absorption, you have all the colors present in white light. Now for copper solution, it will absorb only the red end. That means this zone will be absorbed. So except this zone, rest of the portion will be mixed, and it will give you, that is this part is, sorry, not this part is absorbed. That means rest of the portion, it will be mixed, and it will give you this color, which is appearing as cyan. Now at a first glance it seems that you are seeing only this color, but actually that is not the case. You are seeing this color cyan, which is mixing mixture of all the colors that is remaining. So the mixture of colors is seen by the eye as pale blue, which is also known as cyan. Fine. But in each case, it is really difficult for us to predict that by mixing the remaining color, what will be the overall effect. But to remove that problem, there is an easy way, and that is this color wheel. So from this color wheel, it is very easy to remember. See, when red region is absorbed, you are seeing cyan. When yellow region is observed, you will be able to see the color blue. So the compound, if you are saying that it is appearing as blue color, that doesn't mean that it has absorbed blue color. Actually, it has absorbed yellow color and rest of the part is mixed and it is creating the color blue. Okay. So from this color wheel, you can get some estimation of the color because by mixing the other colors, what will be the color ultimately generated? That is not really possible, not possible for us to predict. But from this color wheel, you can get some idea. That is some estimate of the color using the idea of complementary color. So in this color wheel, the opposite color we call as complementary. So here cyan is complementary color for red, magenta is complementary color for green, and vice versa. That is, green is also the complementary color of magenta, right? Okay. Any doubt? Here we have some examples for different metal ions and what will be their color in the aqueous solution. So see, in the left hand side column you have all the ions. Now here only metal ions are written, ligands are not written, but that does not mean that these metal ions are actually free. Basically, these are the colors that are mentioned here in the last column. That is actually the aqueous solution color. Okay, so that is, it is written color of some hydrated metal ions. So here for simplicity, it is simply mentioned as Mn2, Fe3, Fe2, but actually it is not like this. It is actually surrounded by water molecules. Suppose H2O whole X, and there is some charge present because water is neutral. So if the oxidation state is 2, it will be 2 plus outside the coordination state. So basically all these are surrounded by aqueous water molecules. That means they are hydrated metal. It is not that they are free metal. Okay. So you can consider as if water is the ligand. Now for scandium 3 plus, titanium 4 plus, both are 3d0 system. Now for 3d0, no color possible because no electrons are there. No question of promotion of electron from lower energy to higher energy. Then from titanium 4 is 3d0, so titanium 3 will be containing 1 electron. And now gradually colors are appearing. Now in this way, now see, if when you are you have reached copper 1, copper 1 is 3d10 configuration because copper when neutral it is 3d10 4s1. So when you are moving 1 electron, you will have fully filled configuration 3d10. Zn2 plus is also 3d10. Now see, both are colorless because now all the electrons are paired. You do not have any unpaired electrons, so no question of promotion of it. Okay. So for copper 2 plus, what we have seen that it is absorbing color in the red end, and we are seeing the color cyan. So here it is mentioned blue. Actually, it is light blue. Blue is mentioned. Then see, yellow color. The previous slide it is mentioned. Yellow color, if it is absorbed, then you will be able to see the complementary color, which is deep blue. Okay. So for cobalt 3, you can see this deep blue color is mentioned. Also for chromium 2, deep blue color is mentioned. Though here only blue is written, but there may be different types of blue, light blue or deep blue. Okay. So this table, it is not that you have to remember all the color because that is really not possible, but just to have some idea. Okay, that is when the electronic configuration of in the 3D it is changing, then how the colors are changing. And also for 3D0, that is the where you do not have any electron, or if when it is 3D10, when it is fully filled, all these conditions will give you no color. So some compounds where the scandium 3 plus or titanium 4 plus or copper 1, zinc 2, these ions are present. You will see those salts are complex. They are actually having no color. Fine. So question may be that is based on this topic. It may be that some systems will be given and it will be asked that in which cases it will be colorless. So you have to find in which case the configuration is either 3D0 or 3D10. And also remember one thing, that when it is 3D9, okay, that means one unpaired electron is present. Fine. And when it is 3D1, then also one unpaired electron. That means these two situations are actually analog. So that is why some similarity we will find in the color. That is, if you have two systems, one is having 3D1 configuration, another one is 3D9 configuration, both will be having almost similar color. So that is why see here copper 2 is blue. Fine. Remember copper sulfate solution, it is blue. And similarly here vanadium 4, though titanium 3 is purple, but it is still towards blue. So this is also blue, because same color is possible only when number of unpaired electrons will be same. But that doesn't mean that whenever number of unpaired electrons same, you will get exactly same color. It may not be always, but sometimes it may be the case. Fine. Any doubt? So now we have problem based on this. Which pair of compounds expected to show similar color in aqueous medium? Okay, so same thing we have to do that I have just said. With the option A, you have Fe3 plus and you have copper 2 plus. Now copper 2 plus is 3D9 and iron 3 plus is 3D5. That means not same electronic configuration. And not just, it is not that same electronic configuration. You have to understand how many unpaired electrons are there. In Fe3 plus you have 5 unpaired electrons, but here you have only 1 unpaired. Then option B, here the molecule is VOCl2. Now if you remove Cl2, 2 negative charge you have removed, that means it is vanadium oxygen carrying 2 plus charge. Now if it is 2 plus charge and for each oxygen we know it is minus 2, that means here the oxidation state for vanadium is plus 4. Plus 4 minus 2, overall excess 2 positive charge outside the sphere. Now vanadium, when it is neutral, it is having 3D3 4s2. So when it is vanadium 4 plus, the configuration will be 3D1, right? And other system is copper 2. Now copper 2 is 3D9 that we have seen. Here also one unpaired electron. That means both are having one unpaired electron. So this option may be correct, but we will also see the other two. Option C, cobalt is 2 plus. Now cobalt when it is neutral, 3D7 4s2. That means when it is 2 plus 3D7, 3D7 means how many unpaired electrons will be there? 5 unpaired electron, then 2 will be paired. That means 3 unpaired electron will be there. And Fe2 plus, which is this one, it is 3D6. So in 3D6 you have 4 unpaired electrons, but here you will have 3 unpaired electrons. So this cannot be correct. And the last one, Fe2 plus, again Fe2 plus means 3D6, Mn2 plus. Now Mn when neutral it is 3D7, sorry 3D5 4s2. That means when it is 2 plus it is 3D5. Now 3D5 5 unpaired electron, but here 4 unpaired electron. So in which case you are having same unpaired electron? It is the second system, right? So metal and salt having similar number of unpaired electrons in d orbitals show similar color in aqueous medium, and that is why this vanadium 4 plus it is D1, copper 2 plus is also that is D9, but unpaired electron 1. So that is why correct option will be option B. Okay, any doubt? So this is 3D1 configuration and 3D9 configuration, both are shown here. You can understand that only one unpaired electron is there. Okay. Next property, magnetic property. Magnetic property we have not discussed for S block and P block. Okay, it is also very unique character for D block elements. So why it is the case? The magnetic properties of a compound, they are actually the measure of number of unpaired electrons in it. Okay, if there is no unpaired electron, then there will be different magnetic property. If there is paired unpaired electron, then another type of magnetic property. Now, when a magnetic field is applied, in presence of magnetic field, two main category that we can have, though there are other categories, but these two are enough for us right now in this chapter. One is paramagnetic, another one is diamagnetic. Now, in case of D block elements, most of the compounds are paramagnetic. Paramagnetic character you will get only when there is unpaired electron, and in most cases there is unpaired electron. So that is why most of the compounds of transition elements, they will be paramagnetic in nature, and as a result they will be attracted by magnetic field. But if there is no unpaired electron, it will have diamagnetic nature. So the substances which are repelled by magnetic field, they are called diamagnetic, and this character arises because of presence of paired electron. So only paired electron will be there. For example, if you consider Zn2 plus, which is 3d10 4s0, that means you do not have any unpaired electron. So this is diamagnetic example. Now paramagnetic means now there will be attraction by the magnetic field, and it is possible only when there is unpaired electrons present. Now what is the explanation for this magnetic paramagnetic character? In D subshell, mostly you will see there is partial filling. That means always there will be some unpaired electron. There will be hardly some cases. For example, Zn2 plus, or if you consider scandium 3 plus, then it is zero system or fully paired. In that case, you do not have unpaired electron. But in between these two cases, you will always have unpaired electron. So in most cases, transition metal ions or their compounds, there will be presence of unpaired electrons in this subshell, starting from D1 up to D9. Because if it is D0, it is diamagnetic. If it is D10, it is also diamagnetic. So in between these two, for this range, it will always be paramagnetic because it will always have unpaired electron. Unpaired electron number may change, but at least one unpaired electron is enough to show paramagnetic behavior. Fine. Now magnetic properties, it is denoted by mu value, which is known as magnetic moment, and that is equal to root over n into n plus 2. Unit is Bohr magneton. Now what is n? N is nothing but the number of unpaired electrons. So if you know the number of unpaired electrons, just use this formula and you can get the value of magnetic moment. Paramagnetism arises from the presence of unpaired electrons, and higher is the number of unpaired electrons. That means when n is very high, obviously mu value will also increase. Bohr magneton, that is the unit Bm, and in this table you can see some metal ions in aqueous environment is given. The corresponding electronic configuration, that is 3d1, so see 1 unpaired electron, up to 3d5. Gradually number of unpaired electrons are increasing, but now when you have reached 3d6, there is one pair, so now it is again decreased. Here it is 5, but now it is 4 unpaired electron. Then for 3d7, 3 unpaired electron. 2 unpaired electron, 1 unpaired electron. So maximum value for mu you will get for Mn system, manganese system, right? So it is 5.9, which is basically that is calculated value, experimental value. Experimental value means observed value, that value that you are getting after doing some experiment. It has nothing to do with theoretical calculation. But the left hand side column, the values you are getting by using this formula. And see, in most cases, they are very close to each other. The values are close to each other. That means this formula is giving you very correct result. Okay. So maximum we have reached here, and again it is decreasing. So both sides, when you are moving up or down, it is decreasing because maximum unpaired electron is possible for Mn2 plus. Okay. So if magnetic moment values are given, now from this formula also in reverse way you can also find out the number of unpaired electron. And that is, if mu is given, you can calculate the value of n, and also vice versa, that is, if n is given, you can calculate value of mu. Both are possible. Each unpaired electron have magnetic moment associated with the spin angular momentum and orbital angular momentum. Now electron, when it is revolving around nucleus, it is also revolving in its own axis. So when it is revolving around its own axis, there will be spin motion, and because of that there will be spin angular momentum, but it is also revolving surrounding the nucleus. Okay, just you can compare this type of motion with the motion of the Earth. It is spinning on its own axis as well as it's spinning surrounding sun. Okay, so here also two different types of motions are there, and that is why two different angular momentum will be generated. But this formula, that is root over n into n plus 2, that is based on only spin. We are not considering orbital contribution, only spin. Orbital contribution we are not considering. In the compounds of first transition series, so all these examples, they are first transition series. The orbital angular momentum, there is actually no contribution, and that is why we are not considering it. But except first transition series, when you are moving to the other two transition series, that is second and the third, now magnetic moment arises only, therefore for the first transition elements, magnetic moment arising only from the spin. But if it is second and third transition series, now the magnetic moment, it will also have contribution from orbital angular moment. So that is why compared to first transition series, in case of second and third transition series, their magnetic behavior is very complex. Okay. For heavier transition elements, that means second transition series, third transition series, here what happens? The magnetic behavior is more complex. Here filling of electrons involve 4d and 5d, not 3d, that is for first transition series. Now 4d and 5d compared to 3d, they are too much spread out in space, and as a result, inter-electronic repulsion are very much less compared to 3d orbital, and that is why orbital contribution will be generated. But we are not considering this. This is just the information that you should know. Here mostly you will get problems from first transition series and their magnetic moment, and you just have to use this simple formula where only spin contribution is considered, not orbital contribution, because that contribution is insignificant for fast transition series. Related to magnetic properties, here we have a problem. Magnetic moment given in Bohr magneton unit 1.73. This value will be shown by one of these following compounds, and you have to find which compound is actually correct. Here mu value is given, which is 1.73. So when mu is given, which is equal to root over n into n plus 2. right? Now 1.73, the closest value that is possible, that is in whole number, it is 2. Now if it is sorry, not in this way. Now minimum number of electron, that is just one unpaired electron is in. That means minimum value for n is 1. So when it is 1, it will be 1 multiplied by 1 plus 2, that means 3. So it is basically root 3. Okay. And when n is, this is n equal to 1. When n is equal to 2, now it will be root over 2 into 2 plus 2. That means 2 into 4. So this is root 8. Okay. Now root 8, it will be greater than 1.73, right? Because when it is 2 square, it is 4. Okay. But when you are taking root of 4, you are getting 2. So when it is root of 8, it must be greater than 2. That means it is also greater than 1.7. So a root 8 you are getting when n is 2. That means 2 unpaired electron, this possibility is not possible. But 3, that means root 3, it can be equal, close to 1.7. So what I am explaining all this, because even without using calculator, you can understand that when magnetic moment is 1.73, what will be the corresponding number of n? Because here this side value is given, you have to understand n. Now minimum value possible 1, then after that it is possible, next value possible 2. But when it is 2, it is root 8, which is not possible. That means this will be the correct unpaired electron number. So next what you will do, in which case there is one unpaired electron, that you have to find out. Now for copper 2 plus, because ammonia is neutral. So when it is copper 2 plus, it is 3d9, and in 3d9 there is one unpaired electron. So this will be the correct option. Then nickel. Nickel having 4 cyanoligand, that means 2 negative charge excess. So if it is X, it will be X minus 4 for cyano, overall minus 2. So X is plus 2. That means it is nickel 2 plus system. And nickel 2 plus system is basically 3d8. But in 3d8, it is not that it is having one unpaired electron. That is not true. So this is not correct option. Then we have titanium 4 plus. Titanium 4 plus, it is basically 3d0 system. That means no unpaired electron, magnetic moment 0. Then we have cobalt 2 plus system. Now cobalt 2 plus is 3d7. Now 3d7, how many unpaired electron? 3 unpaired electron. So this is also not correct option. So the copper 2 plus, that will be the correct option. Okay, any doubt? Should I repeat any part? Next question is, the compound which doesn't show paramagnetism. That means no unpaired electron. So another way also the question may be asked, that the compound which will not have unpaired electron, that you have to find. Now see, this question is interesting because option A and B you have D block elements, silver, copper. But C and D, these two are oxides of nitrogen. So you can consider as if this question is combination of two chapters. One is D block, another one is P block. Because in P block we have seen oxides of nitrogen in group 15, because nitrogen is from group 15. Okay. So what about this NO and NO2? Let's see first. So NO, if we consider the bonding, and NO2, 2 oxygen, 1 oxygen. Now nitrogen, number of valence electron is 5. That means 2 electron will be used, nitrogen will use for bond formation with oxygen. 2 electron will remain as lone pair. Number 5th electron will remain as lone electron. It is a lone electron, single lone electron. Okay. Similar, that means it is paramagnetic. it is having odd electron, lone electron or odd electron, so it will be paramagnetic. Now for NO2, 2 electrons used for bond formation with double bonded oxygen. Now the another bond, which as if it seems as if it is single bond covalent bond, but actually it is coordinate bond. And what is the difference with covalent bond? Here both the electrons given by nitrogen. So that is why sometimes you will see NO2 is written in this way, plus minus. So here the fifth electron that will remain as lone electron again. Okay. So covalent bond is suppose bond between A and B. One electron given by A, another electron given by B. But if it is covalent coordinate bond, now both the electrons are given by same element. That is the difference. So here both the electrons given by nitrogen, and the fifth electron that will be the odd electron. So this is also paramagnetic. So these two cannot be correct option, because we have to find which system will not show paramagnetism. Okay, this will show paramagnetism, this will also show paramagnetism. Now come to the D block elements, that is copper. Ammonia is neutral. Chlorine, if you remove 2 chloride, oxidation state will be +2. Now +2 means it is 3d9, and 3d9 means 1 unpaired electron. So this will also show paramagnetism. So obviously one is option B is left, it should be the correct option. But why it is correct, let's see. Here oxidation state is Ag+. Just remember copper plus. It is 3d10 system. That means you do not have any unpaired electron. Ag plus is the same situation because silver is in the same group of copper. Just below copper we have Ag, and after that gold. That means if copper plus is 3d10, Ag plus will be 4d10. Okay, and when it is neutral Ag, it is actually 4d10, 5s1. So when you are removing one electron, because it is +1 oxidation state, it is 4d10. That means no unpaired electron, and no unpaired electron means no question of paramagnetism. So this is the correct option. Okay, any doubt? Sometimes if you can't remember that it is in the same group with copper, but if you can eliminate these 3 options, then you can easily reach option B is the correct option. So sometimes even if you do not understand what is the correct option, just by eliminating the other options also you can reach the correct option. Okay, any part should I repeat? Cold ferrous sulfate solution, that means FeSO4, ferrous, Fe2 plus. Cold ferrous sulfate solution on absorption of nitric oxide develops brown color. This brown color is because of which of these 4 complex? So see, ABCD 4 options, and all the options there is different complex. In none of the option you will find same complex appearing again. All these are different. But these paramagnetic, diamagnetic, A and C para, B and D dia. Okay. So this brown color formation, when you are adding NO2 Fe2 plus, what is actually happening here? Here this type of brown ring. So this test is also known as brown ring test, and this test is mainly done for the identification of nitrate ion, NO3 minus. So suppose if you have any sample where you want to detect whether nitrate ion is present or not, then you can do this test. This is called nitrate test or brown ring test. Okay. So what happens here? NO3 minus in presence of Fe2 plus ion, which is coming from FeSO4, And also here acidic solution is used, so that is why H plus is also present. Now this NO3 minus, it will be reduced by Fe2 plus and it will be reduced to NO. And Fe2 plus, that will be oxidized to Fe3 plus. So this is oxidation reduction. Now this Fe2 plus, that is as you are doing the experiment in water medium. So Fe2 plus, that will be surrounded by water. So that is, it is written as FeH2O62 plus. Now the NO which is formed in the first step, this NO will react with FeH2O62 plus and it will form this type of complex, which is basically responsible for this type of color, that is brown ring. So it is not that whole solution is brown. This experiment you have to do very carefully, otherwise it will not give you correct result. So when it is done perfectly, this type of ring formation is generated. So see here, only a particular layer is brown. It is not that the whole solution is brown. Okay, so that is, it is called brown ring, not brown solution. And the complex is FeH2O5NO. Outside there is 2 plus charge. So it is matching with which option? Can you tell me among options A, B, C, D? Which, just based on this formula, because even you don't have to understand whether it is para or dia. Even without knowing that also you can choose the correct option, because all the 4 molecules that are given, all are different. So with which it is matching? Any of the options? Outside charge is 2 plus. So that will be balanced by sulfate ion or nitrate ion. Here you have 1 sulfate. Now sulfate is carrying -2 charge. This is also 1 sulfate, but inside you have N3. So this is not correct. Then here we have 2 sulfate. That means total negative charge -4. But here you have only 2 plus. That means this will be correct. That is the option A. So even if you do not know whether it is paramagnetic, then also you can choose the correct option, which is option A, if you know the formula. But if you do not know the formula, then on the basis of then no question of understanding whether it is para or dia. So first you have to understand what is the formula, because if you know the formula, then only you will be able to understand what is the oxidation state of iron. And if you know the oxidation state of iron, then only you can understand how many d electrons are there, and depending on that you will be able to understand whether it is paramagnetic or diamagnetic. Okay, so though we know it is option A, but we have to understand why it is paramagnetic. So nitrate test is done by the addition of FeSO4 to the nitrate solution, which is basically your sample. So if you do not know whether your sample is containing NO3, it will be the unknown solution. So you just add FeSO4 to this unknown solution. If NO3 ion is present, it will act as oxidizer. It will oxidize Fe2 plus to Fe3 plus. Okay, and hence it is detected by utilizing this property. That means as nitrate has oxidizing property, you can utilize that property to do this test. Now we will see the configuration. Here outside charge mentioned 2 plus. That means what will be the oxidation state of iron? It is actually +1. Now why it is so? Because water is neutral. And NO, though it is a special case, and you will hardly see this type of example where ligand is carrying some positive charge. So mostly what we know, ligands, they are either neutral, ammonia, water like this, or they are containing some negative charge. But NO is a specific case which is containing +1 charge. So +1 charge for NO, from NO, and +1 from Fe, overall charge is 2 plus. Now if iron is having oxidation state +1, what will be the configuration? It will be 3d6 4s1, because you have just removed 1 electron. Now 3d6 4s1 means 7 electron. Now all the electrons, that is this electron also, it will be promoted to 3d, and now 3d there is total 7 electron. And why it is promoted to 3d? Because we need sp3d2 hybridization for octahedral geometry, and for that we need vacant 4s. So that is why the electron from 4s is transferred to 3d, and you have total 7 electron in 3d, and there are 3 unpaired electron, that is responsible for this paramagnetic behavior. Option C is also paramagnetic, but this is not having correct formula for the complex. So that is it is not the correct option. Option A will be the correct option. So regarding all the slides, is there any doubt? Because we are at the end of the session. So if you have any doubt, please mention. So we are ending the session here as there is no doubt. Thank you for listening.